Okay, so reducing the length of 50 by 150 foot rectangle by 10 feet, keeping the same perimeter, which again means like you need the same amount of fence, right? Keeping the same perimeter. There it goes from 7,500 to 8,400 square feet. So change in area is plus 900 square feet, right?
The day opened with a service at St. John Episcopal Church in Washington.
Change in length should be obvious, it's negative 10 feet. If we reduce the length by 10 feet, the change in length is negative 10 feet, right? So the average rate, which is an abbreviation for average rate of change of area with respect to length, right? We have to have those words, and you want to get used to writing them and thinking them. It's, again, to remind ourselves, change in area divided by change in length, and that's plus square feet over negative 10 feet, which is negative 90. And I'll just write it as square feet per foot, square feet of area per foot of length. Now it's maybe a little counterintuitive because your area went up when you reduced the length, okay? So it seems like the area is increasing. Why should the rate be negative? Well, it's because you decreased the length. Okay, if you had increased the length from 140 feet to 150 feet, your area would have gone down by 900 square feet. And you can see this by doing the fundamental triangle. So what have you got? You've got 150. Actually, I want to do the 140. 8,400 here. So the 150 would go to the right of the 140 if you have the length axis going the way it's indicated. Let me make sure. Yeah, I've got it. Okay. Since I moved the board over a little bit, I wanted to make sure I was still focused on that. Still had the board inside. Okay. So the 150, your first coordinate is going to go to the right of the 140, right? And if you don't draw it that way, then you might be confused by some of the numbers, although formally there's no reason it won't work as long as you have the right coordinates. Okay? Anyhow, we have this. So now we sketch our fundamental triangle, and just about everybody had the right fundamental triangle. So the rise is negative 900 square feet. The run is 10 feet. The slope is this divided by this, negative 90 square feet of area per foot of length. Okay? Now if we put these together on our graph, well, here's our graph. I'll just kind of move this over. I think it's visible. Okay, we've got the 8,400. Meaning, of course, 8,400 square feet with the 140 here. Okay, so we're going to have a point here. Now, is the graph steeper from here to here or from here to here? Now, I don't mean does it look steeper, I mean is it steeper? Because I drew those points, I could be off. Like I think I've got that middle point a little bit low. Okay? Well, we know that from here to here, the slope is negative 90, and from here to here, the slope is negative 110. So what's happening to this graph? Is it tending to curve downward, be straight, or curve upward?
Curving down.
I'm sorry?
Curving down.
Curving downward, why? Because this one is steeper than this one and it's going down, right? Now you have a negative slope, so actually numerically the slope here is less than it is here, but they're both negative, so you got to think about how steep they are, right? So the number 110 tells you how steep it is, the negative tells you it's going down, right? So this one is steeper than this one, they're both going down, so it's going down faster and faster. Okay? That makes sense? Everybody understand that? Okay, well, we'll see. Okay? If I find that you don't understand it, we'll come back to it. Okay. Well, that's all very interesting, but really, you know, what we want to know is on the whole, okay? Now, if this is, say, 150 here, 160 here, 140 here, and the graph is, I'll exaggerate the steepness. If the graph is doing this sort of thing, well, that's not very good, but okay. If the graph is doing this sort of thing, tending to curve downward faster, what does this tell me I ought to be doing to my length to get the maximum area? Do I want to keep increasing my length? I'm going to dive bomb right into the axis and have nothing left. By the time my length is 200, my width is 0. I have no area. I have a line with no dimension, well, with no width, right?
I mean, you keep going,
okay.
You might get an extra dimensional space.
You probably nah, probably not. I don't think the law would be able to handle that. I think if I claimed that, they'd probably commit me someplace. Okay. If I could find a lawyer to take the place, they'd probably commit him or her too. Okay. Okay, so it looks like I want to go this way. Because if I go this way, my area is increasing, right? Now, does my area keep increasing?
Probably not.
Is there a limit? If I keep decreasing my length, how much could I possibly decrease my length?
To nothingness.
I could decrease my length all the way down to 0 and have something really wide, but with no thickness, right? So my domain for this function, it turns out, has to end at 200. Now my scale isn't good, you know. If that's 40, that ain't 10. But you get the idea, right? Yeah, we're just trying to ballpark this thing. Also, if my length goes down to 0, I've got no area, right? I've got a very wide lot, and I just need that whole 400 feet of fence just to run up my line and back down the same line. It's going to be difficult to get the fence to occupy the same space. which is what it would involve. Well, what do you think the graph is going to look like? Sketch it for me.